Welcome back everyone. So we were actually trying to understand the group of isometries of R2. So in the process we realized that to understand the group of isometries one need to understand the isometries that fixes origin. We saw that they naturally arise from these orthogonal matrices. So we call such maps as orthogonal maps, and then in this lecture we will try to understand them. So once we understand the orthogonal maps, then it is clear that any given isometries is just a composition of translation and these orthogonal maps. So from that we can actually very well get all the information about like for example the physical interpretation of those maps and so on from these informations. Okay, so let's start with some orthogonal maps and then try to understand what they mean. Okay, so recall so we are interested in understanding an isometry that fixes origin. So let's take F, which is an isometric, and assume that f of 0 is 0. So this is an isometry that fixes origin. So then there exists unique matrix A from GL2 of R such that A transpose is identity and this map f of V is given by AV. Okay, this is the important thing. So we call such maps orthogonal maps. Okay, so we call such F orthogonal. Okay, so that is our definition of orthogonal map. So now we want to use this information about A and then try to kind of explicitly determine so what they do on R2. So take this A transpose equal to identity. So we already know that if you write A as this A B C D, so then these these columns they must be orthonormal vectors. Okay, so that is what we already observed. So this A, B and C D, so they form a orthonormal vectors in R2. So in particularly we can see that the determinant of A square or the square of the determinant, so that is going to be 1. So then that forces that the determinant of A, it can be either plus 1 or minus 1. So only two choices are there. Okay. So now let's write down all the properties. Okay, A transpose being identity, what does it mean? So that means you take A B C D. Okay. So maybe I did the other way. So let's rewrite this. So A transpose A equal to identity. So that means A B C D and then A B C D. So this is going to be your identity matrix 1 0 0 1. So this gives us the following relations: A square plus B square is 1 and then C square plus D square is 1 and AC plus CD, that is going to be 0. So these are all the three conditions. So this indeed says if you take this vector V, which is A comma B, okay, and then this vector W, which is C comma D. So then these vectors satisfying the following property: the norm of V, norm of W both are 1 and V dot W is 0. So they are orthonormal vectors. So this is the data that encoded in this map. So now let's try to understand what happens when the determinant is 1. The determinant of A, if it is 1, so then you can see that you can write A in terms of this cosine maps. Okay. So because this A square plus B square, this is being 1, so you can just rewrite that A equal to cos theta and then b equal to sin theta, okay, because this a comma b is going to lie in a circle. So, this is where the circle S1. So, this a comma b will be somewhere here. Now, if you take this c comma d, so this is going to be just a perpendicular vector, that is all. Okay. So, this is going to be somewhat perpendicular to this a comma b. So, this is going to be c comma d here. So, this should be perpendicular. So, because this is what this orthogonal relation says, v dot w is 0. So, that also should lie in the unit circle, and that is perpendicular to this. Then if you just work it out, you can see that the only possibilities that you have. So, there are two possibilities that you can have. Okay. So, if you take this perpendicular line that is perpendicular to this point a comma b, so then you can draw this line. So, this entire line you can draw. Okay. This entire line is going to intersect the unit circle at exactly 2 points. So, one is this c comma d, another one is the opposite of that. Okay. So, but now what is given to us, this determinant is being 1. Okay. So, then if you a minute thought will simply tell you. So, first of all let us see that what this c comma d being perpendicular tells us. Okay. So, this a comma b perpendicular to c comma d. So, that means the choices for c comma d, the choices for c comma d has to be either this the tuple minus sin theta cos theta. Okay. So, in that case you get cos theta minus sin theta plus sin theta cos theta, okay, or it can be sin theta minus cos theta. So, these are all the 2 points. So, that will be perpendicular to AB. So, now you have to decide which point that you will be getting for this CD, because CD has only 2 choices, either this point or this point. Okay. Now, this determinant of A being equal to 1 determines which point that you can choose. So, you can easily see that the matrix is nothing but cos theta and then sin theta. Okay. Rewriting. So, this is my matrix. So, my matrix A is A B C D. So, this is cos theta sin theta, and then you have. So, if you take for example, the first one, you get minus sin theta and then cos theta. But if you take A to be this, then it is clear that the determinant of A is 1, which is cosine square theta plus sin square theta. But if you take for example, determinant being minus 1, okay, this is if and only if this, then if and only if A will be the other one, cos theta sin theta, and then here you will have sin theta minus cos theta. So, then the determinant is minus cosine square theta plus sin square theta. So, which is minus 1. Okay. So, basically depending upon the determinant, you will be making the choice for C comma D, and that is actually unique choice, because it comes from the perpendicular line perpendicular to the point A comma B that intersects this circle S1. Okay. So, in the case 1, when the determinant is being 1, let us see what A does. So, A is nothing but cos theta sin theta and then minus sin theta cos theta. So, if you just think about it, then A some V will be. So, if you take V to be x y, so then this A V is going to be just cos theta minus sin theta cos theta times xy. So, which is exactly that v times e power I theta. Okay. So, this is going to be the rotation. Okay. So, I will leave it you to just check, okay, from the pictorial point of view what exactly this multiplying by A does. Okay. Indeed, if you take this R2 plane, okay, then you take some vector here v. Okay. If theta is the angle that you are rotating it by this, then you rotate this v in the counterclockwise. Okay, here your AV will be there. So, this is going to be your AV and this is going to be your V and this is the angle theta that you will have. So, you rotate, so basically in the counterclockwise. So, in this case, so what you get, this f of V equal to AV is nothing but a rotation, of course, in the counterclockwise rotation by theta, okay, in the counterclockwise. So, that is the physical interpretation of this orthogonal map when the determinant is 1. Now, what happens when determinant is minus 1? So, let us look at it. Okay. So, when you take the determinant of A is minus 1, so then if and only if, then A looks like cos theta, sin theta and then sin theta minus cos theta. Okay. So, then basically what happens, so let me draw a picture. Okay. So, the plane looks like something like this. So, then what you do, you can actually draw a line which passes through origin that makes angle theta by 2 with respect to x axis. Okay. So, you draw this line. So, this line makes angle theta by 2 with respect to x axis. Okay. So, then when you take this f of v equal to a v, what it is? It is indeed a reflection. So, this is a reflection about this line L. Okay. So, basically this particular formula that actually corresponds to this. So, let us see how it is done. Okay. You take V here, okay, then if you reflect, so you reflect here. So, this is going to be your AV. So, this is your vector V. Okay, I am drawing very bad picture. So, if you take this vector V, so then the reflection is going to be this. And similarly, if you take some W here, so its reflection is going to be somewhere here. This is going to be AW. Okay. So, this is the physical interpretation of this particular map, okay, which is given very explicitly using this matrix. Okay. So, let us actually verify this, okay, because this is something I believe you are seeing it for first time. So, what we want to say, if you take a line that makes angle, okay, theta by 2 from the x axis, then if you reflect with respect to that line, then that reflection as a linear transformation has exactly this particular matrix form. Okay, that is what we are claiming. Okay, so let's try to actually verify this. So, we will do this in general. Okay, we will take some line that makes angle phi, okay, and then try to do it with that, because this theta by 2 you can substitute phi equal to theta by 2. So, now you take a line, let us call it L, and then let us say it makes angle phi with respect to x axis, and what we want to do, we want to reflect with respect to this line L. So, what is that reflection? Okay. It is a reflection with respect to line that passes through origin. Okay. So, that is supposed to be a linear operator. Okay. That also follows immediately from the analysis that we are going to do now. So, this is the line we have picked already. Okay. So, now what we do, we pick a unit vector on this line. Okay. So, call it u1. So, this is your unit vector u1. So, because this is an unit vector and the angle is phi from the x axis, then you can see that this unit vector u1 look like cosine phi and sine phi. Okay. So, this is going to be your unit vector. So, now what you do, you take this perpendicular line and then choose a vector in the opposite direction. Okay. So, like I said, you look at this unit circle that passes through this u1. Okay. So, now if you take the perpendicular line that is perpendicular to this u1, then it will intersect that circle exactly at 2 points, but we need to choose a point that gives the determinant -1. So, that we know already what it is. So, you choose this u2 which is minus sine phi and then cos phi. Okay. So, that is the point that we choose. So, let us cross check. So, okay, this is the opposite point that I am choosing. Okay, anyway, it's not a problem. So, this is the point maybe I will choose. So, this is going to lie here. So, this is going to be your circle, and this u2 is going to lie here. So, this is your u2. Okay. So, all important is they are orthogonal to each other. Okay. So, now if you take some vector, okay, let us call it v, okay, then you want to find the reflection with respect to this L, okay, where it will be sent, which you call it SV. Okay. So, now what is the formula for SV? Okay, let us draw some parallelograms and then try to complete it. Okay, maybe let me use this black. Okay. So, this is going to be your V. So, this V you write it as some C1 U1 plus C2 U2, because U1 U2 both are unit vectors, they are orthogonal to each other. So, they form a basis for R2. So, you can write it. Okay. So, in particularly if you project V on this, okay, so this is going to be your C1 U1, and similarly if you project it here, if you extend this line, if you project it on this, then this is going to be your C2 U2. Okay. So, now you are interested in computing what will be the V. So, this is your V, this is your vector V. Okay. So, now what will be the parallelogram, because the V is obtained from summing C1 U1 plus C2 U2. So, this is the parallelogram that you get. So, this is the complete parallelogram. So, now what you want to do, you want to reflect this V with respect to this capital L. So, you are getting this SV. So, let us see how one can get SV. The best way to get SV, you complete this parallelogram. Okay. So, you go from C1 U1 to this SV and then see where you are coming here. So, this is going to be just the opposite of this C2 U2. So, this is going to be minus C2 U2. So, then if you complete this parallelogram, you can see that this SV has to be C1 U1 minus C2 U2. So, that should be the very explicit formula for this SV. Okay. So, now by writing this V very explicitly, you can see that V equal to, okay, maybe let me use blue. So, this V equal to C1 U1 plus C2 U2. So, these are all the two basis vector that we are keeping it. So, then you write this cos phi and sin phi as AB, and then minus sin phi and cos phi will be minus BA. So, then you can easily see that from that. So, this is going to be A minus B, B A, and then C1 C2. So, this is going to be the coordinates, okay, with respect to, like here you have written it for coordinates with respect to U1 U2, but using the matrix form you can see that V is exactly equal to this. Okay. So, this is exactly equal to C1, okay, AB plus C2 minus BA. So, this is with respect to that usual Cartesian coordinates. So, similar way we can compute what is SV. So, SV is going to be what? This is going to be C1 U1 minus C2 U2. So, then if you do the computation you can see that this is going to be exactly equal to AB B minus A C1 C2. Okay. So, now if you work it out, so then you can see that this is exactly equal to AB B minus A times, okay. So, because so this V is exactly this A minus B B A acting on C1 C2. So, you can invert it. So, you write this as A minus B B A inverse C1 C2. So, basically you are rewriting everything in terms of this this V, okay, sorry, C1 C2 you want to replace. So, this is going to be V. So, because this is V, now if you do the computation, because this is just come from this, okay, from this you can see that A minus B B A inverse V is going to be C1 C2, that is what we are using. So, from this you can see that S of V is going to be exactly, so I will leave it you to do the calculation, then it is A square minus B square 2AB and then 2AB and then minus A square minus B square of V. So, you are interested in writing down SV in terms of some matrix times V, okay. So, that is why we are doing this calculation. Then from this you can see that we got the matrix what we wanted. But what is A? A is cosine phi and B is sin phi, okay. Now, use this cosine sine formulas, then from that you can easily see that A square minus B square is going to be cosine 2 phi, and then 2 cosine phi sin phi is going to be sin 2 phi, and so on. So, then if you replace that, then you can easily see that S of V is going to be exactly equal to cosine 2 phi and then sin 2 phi and then sin 2 phi and then minus cosine 2 phi. Okay. So, this is going to be the matrix very explicitly which is acting on V. So, that means this operator which you have defined using the reflection, okay, which is about the line that passes through the origin, is given by this matrix very explicitly. Okay. So, now this matrix is the matrix that you are getting in your calculation when determinant is minus 1. So, when determinant is minus 1, you are getting exactly the same matrix cosine theta minus cosine theta. So, that means your 2 phi is theta. So, that means phi is your theta by 2. So, you take this line that passes through origin which stays theta by 2 away angle away from x axis. Then if you do a reflection with respect to that, then exactly you get this formula. Okay. So, this actually tells you that when you take these orthogonal maps, so then whenever determinant is 1, that corresponds to a rotation, again about the rotation by theta in the counterclockwise about the origin. This is also a linear operator. When it is -1, so it is a reflection about the line that L, which is defined here. Again that line is also passes through origin. So, this reflection is again a linear map. Okay. Maybe it will be a fun to do these things very explicitly using geometric properties. Okay. Maybe you should try to prove directly that if you take a reflection about this line that passes through origin, that must be a linear map, and as well as if you take a rotation about origin, that also will be a linear map. You can directly try to give argument using geometry. Okay. Maybe you can take it as exercise. So, from this what we have concluded so far. So, we want to understand general isometries of R2. Okay. So, we already observed that given any isometry of R2, it looks like f of v equal to AV plus W. So, for some fixed capital A, which is an orthogonal matrix. Okay. So, now given this data, for various choices of this A and W, we want to conclude what type of isometries that we get. Okay. So, here is the list. Okay. So, here is the isometric, and then let us see what it corresponds to. Here is the condition. Okay. So, first thing is one can take A to be identity and W to be 0. So, that is going to be just a translation. Okay. That is just identity. So, for example, you can take A equal to identity. So, this is going to corresponds to just translation. If you take W again 0, then that corresponds to identity. So, identity you get when you take A equal to identity and W equal to 0. So, now if you take W 0, so what we have seen, and then determinant of A is 1, then you get what is called rotation, but rotation about the origin, about the origin. So, that is what we will get. So, this is something we already proved. So, now if you take W 0 and determinant being -1, so then this is a reflection again with respect to this line, with respect to a line that passes through origin, and makes theta by 2 angle with x axis. Okay. So, that is your determinant A equal to -1 and W being 0. So, now let us look at that condition when W is non-zero and then see what happens. Okay. So, if you take still this rotation. Okay. So, now for example, if you take determinant of A just being 1, then the f of v looks like AV plus W. Okay. This is what we are getting. So, if you forget this translation, so then it is just a rotation, but if you compose, okay, this can be written as follows. This is T W of AV. Okay. So, basically you are composing, okay, two maps. Let me rewrite T W, some let us call it f tilde of V, where f tilde of V is given by AV. So, this is your f of V. So, now you see that this is composition of two maps, this f tilde which corresponds to the determinant A being 1, this is supposed to be a rotation about origin. Now, if you take a rotation about origin and then translate further, then all you are going to get again a rotation, and that rotation now is not about origin. So, that is now about this f of 0. So, that means in this case f is going to be a rotation about, so f is a rotation again about some particular point. So, that is going to be a fixed point P. Okay. So, we have to calculate what is that fixed point about P, where f of P should be equal to P. So, I will leave it as exercise, you can calculate very explicitly. So, P is going to be just I2 minus A inverse W. Okay. So, this is something you can check directly, but it is clear from the formula. So, once you take a rotation about origin and compose with translation, then you will again get a rotation, okay, and that rotation has this very explicit formula, and that is rotation about some point P, that point also given very explicitly using this formula. Now, let us look at what happens when determinant being minus 1. So, when determinant is minus 1, again you will be having f of v equal to a v plus w. You can write again f equal to some t w composition f tilde, where f tilde of v is given by a v. So, now this v goes to a v, that map is a reflection with respect to a line that passes through origin. Now, if you take a reflection with respect to a line passing through origin and then translate that one, then what you are going to get? You are going to get again a reflection with respect to some other line. Okay. So, then it is clear that in this case we get again a reflection. Now, you can actually work it out. So, what will be the line that with respect to you will be doing the reflection? Of course, the line of reflection is going to be a fixed point subset of this R2, that is fixed by this f. Okay. So, basically the line of reflection is going to be those P in R2 such that f of P equal to P. So, I will leave it as exercise, okay, you can just figure it out. So, this is going to be exactly equal to omega by 2 plus kernel of A minus I2. So, note that this kernel of A minus I2, it is going to be a line, okay, because in this case this A minus I2 will not be a invertible map, but in the previous case it is an invertible map. So, here it is invertible map, but in this case this is not invertible map. A minus I2 is not invertible. So, and it is also not 0 map. Okay. So, A is being non-identity. So, it is not 0 map. So, in particularly the kernel will have dimension 1. So, this will have dimension 1, it is a line. So, now you translate that line by omega by 2, then you get the line of reflection for this reflection. Okay. So, this says, so you get isometry, the corresponding condition is the following. So, when determinant is 1 and of course, A is not equal to identity, you are going to get rotation. Okay. And when determinant is minus 1 and you can see that this A omega is also A w is also supposed to be minus w. Okay. So, then you get reflection. So, this is reflection with respect to a line passing through origin. So, because when you substitute f of v, that is going to be AV plus W, then f of W is going to be AW plus W. You demand this f of W is 0. So, that means AW equal to minus W. Okay. Because of this you can see that, so this is not correct. So, it is just a reflection with respect to a line. So, that is what you get in this case. So, I guess that is what I told here, but you need to be bit careful. So, yeah, maybe you can actually think about it. So, in this case you get a reflection with respect to just a line. So, when this condition is not satisfied, when determinant of A is minus 1, but AW is not minus W, then what you get is actually glide reflection. So, glide reflection is indeed composition of a translation and reflection. Okay. So, here we got that f of W is 0, but in this case we demand f of W is non-zero. Okay. So, more or less you can take the definition of glide reflection to be this, no issue. Okay. But of course, it is important to figure out what this means geometrically. I will leave it to you to actually figure it out. Okay. So, these are all the only possibilities that we have. Okay. In all these possibilities, so we have interpreted physically what happens to those isometries. Okay. Okay. So, again if you take this bigger group isometries of R2. So, as we noticed, there are two already important subgroups that we have seen. One is O of R2 that naturally sits inside isometries of R2, and there are these translations. So, TV V comes from R2. So, this also sits inside naturally inside isometries of R2. So, if you think about it, these translations, so they are naturally isomorphic to R2, because given any V you have this TV, and that TV actually like behaves exactly as the vector V. Okay. Whenever you add the vectors, the maps also get composed. So, these two important groups are there, and somehow these two groups actually kind of produces all other isometries. So, what is the meaning of that? It means when you take the product between these two groups, so then that will be exactly equal to isometries of R2. Okay. So, maybe you can try to check that. But what we will be interested in the later class, so I will again spend one more class on this isometries of R2, and I will actually try to study all the finite subgroups of this isometries of R2. Okay. So, our ultimate goal to understand all finite subgroups of this isometries of R2. Okay. So, we want to look at all possible finite subgroups of isometries of R2. For example, if you start with a rotation that has a finite order, so then if you take a cyclic subgroup generated by that rotation, that is going to be finite subgroup of this isometries of R2. For example, you can take theta to be some 2 pi I divided by n. Okay. So, sorry, 2 pi divided by n for some fixed n in n. Then consider this rotation with respect to theta about the origin in the counterclockwise. Okay. Or you define this r theta of z to be z times e power I theta. So, then you can easily see that r theta power k of z is going to be just z times e power I k theta. So, now r theta power n z is going to be exactly z e power I 2 pi by n times n. So, then this is going to be exactly equal to z times 1, which is z. So, that means if you take this r theta subgroup generated by r theta, so this is going to be a finite subgroup of this isometries of R2. Okay, so there are other important finite subgroups of isometries of R2. So, they are called dihedral groups. Okay. So, they appear naturally as isometries of what is called this n-gon. Okay. So, maybe I will actually talk about it in the next class. I will stop here. So, we will talk about this isometries of this n-gon in the next class. Okay, thank you.